Okay, welcome. So let's make a quick review of our last lecture. If you remember, I was talking about the three-dimensional effects, and let me just go down. Okay, well, first of all, in the majority of our performance calculations, we consider what we call the longitudinal motion. And in this case, we assume that the aircraft is moving in a plane only, in this vertical plane. And that is called the longitudinal motion of an aircraft. So in this plane, there are 2 degrees of freedom. There are 3 degrees of freedom. It can go up and down the vertical axis. It can go along the horizontal axis. These are 2 degrees of freedom. And then there is a rotational motion, which is the pitching motion. And the other motion of the aircraft are not a part of the longitudinal motion. And in this to study this motion, we need to know the forces that you see on this diagram. So the aerodynamic forces included in this motion are the lift and drag forces, for which we use these equations, and the aerodynamic coefficients, which include the information about the design of the aircraft, are these 2 coefficients, CL and CD, lift and drag coefficients. Okay, and okay, so when you have a real three-dimensional aircraft, due to the vortices created at the wingtips, these coefficients differ than those for a 2-dimensional airfoil, and the difference in the drag coefficient is, well, the drag coefficient is composed of 2 parts. The first part is the part that is independent of the lift force, independent of the lift coefficient. We call this part the parasite drag or the foreign drag. And the second part is a function of the lift coefficient. So when you have no lift, there is no wingtip vortices created, and in this case there will be no additional drag. In this case, the drag force is only this part. But whenever there is a lift force, the lift force is created by the pressure difference, and the same pressure difference creates these wingtip vortices, and this effect creates some additional drag, and the drag component is called the induced drag component. Okay, and I said that this dependence is known to be quadratic. Okay, so this is known from many experiments performed, and also some theoretical analysis, which I didn't explain what they were. But what you need to know for this course is that the drag coefficient changes with the square of the lift coefficient. And if you plot the data on a graph, you get such a parabolic relation, and you can express such a parabola with this equation. And the coefficients here, A and B, are dependent on the aircraft type. So if you have test different types of aircraft, you will get different curves. They will all be parabolic, but they will have different A and B coefficients. So for a specific aircraft, you need to know the values of these coefficients. So the A coefficient itself is equal to the parasite drag coefficient CD0, and for the B coefficient, there is an expression, and let me skip to that expression. The B coefficient is given by this relation here. So this forms the B coefficient, and if you look at this coefficient, there are 2 parameters related to the design of the aircraft. One is the aspect ratio. The other is a non-dimensional quantity called the Oswald efficiency factor, E. Okay, so the E can take a maximum value of 1, and that 1 represents an elliptical wing planform. And for any other planform type, it is a number less than 1. And for rectangle, for example, it is known to be about 0.7. So this is basically what was discussed on Tuesday. So today I would like to start with an example problem. So this is similar to what you will do in your second lab experiment, or second or the third one, I'm not sure. You will be doing the second experiment on a different wind tunnel in the aerodynamics lab. And in that wind tunnel you can measure lift and drag forces. And if you do that, you will, in that experiment, you are supposed to obtain curves like these here. So let me just make this slightly bigger. Okay, so this curve, the one on the left, shows the lift forces. So these are dimensional values directly. They have the unit of newtons. And these are measured at different angles, right? So you put your test model at different angles. You take a measurement, you change the angle of attack and take the measurement again. So if you do this a number of times, the data you will get is supposed to look something like this. I'm not sure how clean the data you obtain in that tunnel will be, because I haven't done this experiment myself yet. But hopefully you will get such a relation for lift versus angle of attack. And at the same time, you will be measuring drag forces as well. And the drag forces should look something like this as well. And so let's see what you can do with these data. Suppose that you made the experiment and you obtain these two data curves. And from here, you can compute the drag polar coefficients, right? So in the question it says, assuming that the drag polar of the aircraft is given by the following equation, find the present drag coefficient and Oswald efficiency factor for this aircraft. So this is the drag polar equation, and from the data you measured in the wind tunnel, you are asked to calculate this value, the Oswald efficiency factor, and the present drag coefficient. Okay. Okay. Well, first, since these are obtained as dimensional forces, the first step should be to calculate the corresponding aerodynamic coefficients for these values. Okay, so these are dimensional, these have the units of newtons directly. So from here, the first step should be to calculate the non-dimensional coefficients. And to calculate the non-dimensional coefficients, you'll be using these equations. So this is what you measured. And you should know the speed of the test and the air density. Now from here, you can calculate the lift and drag coefficients. So for example, if you do this for the first this point here at -2 degrees, you see the lift force was measured as 0 and the drag force was measured at 0.1 newtons. So for this these 2 points, the corresponding aerodynamic coefficients are calculated as for CL it is 0 because the lift force itself is 0, and the drag coefficient is 0.028. So if you insert these numbers into the drag polar equation, which is this equation here, so this is equal to 0, and this is 0.028. So from that you get the present drag coefficient as 0.028. Okay, so this is the present drag coefficient, and next you are asked to find the E value. To find the E value, you need to choose a data point for which lift is different than 0. So you can use any of the points here to calculate the E coefficient. Let's see, and I think we picked the one at 14 degrees. So at 14 degrees, the lift force was measured as about 5 newtons, and the drag force was measured as 0.5 newtons. And if you put those numbers, you calculate the coefficients as these values, 1.4 for the lift coefficient and 0.14 for the drag coefficient. Again, you put these numbers into the drag polar equation. This is the drag coefficient, lift coefficient, and the aspect ratio can be calculated because we know the wingspan and the wing surface area. And that gives us an aspect ratio of 7.36. And if you put everything in that equation, the Oswald efficiency factor turns out to be 0.76. Okay? So this is how this direct polar equation is used in a practical application. So I just made up these numbers. So these data does not really correspond to a real aircraft. But if you had a real aircraft, for example, from this calculation you can obtain the span efficiency or factor for your design. So for this design, that happens to be 0.76. So there's a note here which is important. To be able to claim that above number is a true Oswald efficiency factor, the wind tunnel test must have been performed without any wall effects. So for example, if the test was performed in a configuration similar to this, then you can't claim that that's a realistic number, because here the wall effects will be too strong. So the model is too close to the ground, and there's no place for vortices to be freely created at the wingtips. So obviously the data you collect in a test like this does not give you realistic numbers. But if you have a model that fits into the tunnel as this one here, then this is much better, because you have much more space between the model and the walls of the tunnel. So the wall effects will be much smaller in this case. And let's see, that was the second part of this problem. Okay, so you test this aircraft in the tunnel and obtain this data. And in the second part it says the real aircraft with a mass of 2,500 kilograms is flying at an altitude of 4,000 meters at a speed of 100 meters per second. What should the angle of attack be so that the aircraft can maintain its altitude? And how much thrust force should its engine provide so that it can keep its speed? Okay, so we should find the necessary lift coefficient for this case. We know the weight, and the lift force created should be equal to this weight value, so that there will be no vertical acceleration. So this is the lift expression, and we equate the lift value to the weight of the aircraft. Again, you should remember to convert the weight, the mass value to weight by multiplying it with the gravitational acceleration value. So from here, the necessary lift coefficient is found to be 0.37. And this is the air density value. Since the aircraft is given to be flying at 4,000 meters, the density value at that altitude should be known. And that value is taken from the standard atmosphere table as this much. And the lift coefficient is 0.37. So this plot is given in terms of dimensional lift values. So you should convert this to non-dimensional lift coefficient values, and then from there you will be able to get the corresponding angle of attack. Okay, so I will post this the sample problem so you can study it later on. And again, there's an important note here regarding the Reynolds and Mach numbers, so you should be careful about that as well. Okay? Are there any questions? Okay, so let's start talking about the standard atmosphere. So I don't know if you paid attention, but in our aerodynamic equations, we have the air density value. So in the previous problems, I was using this number, 1.225. So this is the air density, the average density value of the air at sea level. But in the problem, a different value was used. It was 0.82, and this is the average air density value at 4,000 meters altitude. And so where did I get this value? I took that value from a standard atmospheric table, so which is what I would like to talk about today. Aerodynamic forces obviously depend on air properties, and air density itself directly appears in the equations. So in these equations, we need to know the value of the air density, which is represented by this Greek letter rho in our equations. And air properties, including its density, depend on a lot of different factors, right? So let me come back to the previous page. So air temperature and pressure depends on altitude. It depends on location, time of day, season, solar activities, etc. There are a lot of things that affect these air properties. So for example, the air density here in this room is not exactly equal to the air density outside the building, right? And also air density outside the building will be different than air density in Istanbul, for example. Or even within a certain city, due to a lot of different reasons, these properties change. And it's really impossible to know the exact density without actually measuring it beforehand. So if I want to make some aerodynamic calculation in this room, I can take some measurements and I can calculate, I can know the air density and use that. But to be able to predict the aerodynamic forces in somewhere else, I need to know the exact value in that location. But all these factors that affect the air properties, like time of day, season, solar activities, these are impossible to predict, because most of these things are not even deterministic. These are random effects, right? So you can't really know what the air density will be. So what we do is, well, whereas most of these factors are not easy or even impossible to predict, the variations of these properties, as most importantly the air density with altitude, is fairly uniform and it's easy to predict. So what I'm saying is, so if this is the Earth's surface, so I can't exactly tell how air density changes on the surface of the Earth. The changes with the altitude are much more predictable. Okay, so if I go 100 kilometers towards north or 100 kilometers towards south, I can't tell how much the air density will change, or if it will change at all. It may be increasing slightly, it may be decreasing slightly. But I know that if I climb by a certain amount, there will be certain predictable changes in air properties. And this is what we use in our calculations. Okay? So in other words, we completely ignore the changes on the surface of the Earth, and we only take the changes with altitude into account in determining air property values. So it's impossible to take into account all these factors when designing and analyzing flight vehicles. And standard atmospheres are defined to form a common reference for mean values of temperature, density, pressure, etc. as functions of altitude. Okay, so let's start with air pressure. Well, in our equations, we need air density. Right? Density is the only thing that appears directly in our equations. But Temperature and pressure are important as well because they affect things like air viscosity and speed of sound, and these quantities are important in calculating Mach and Reynolds numbers, right? So even though density is the only thing that appears in our equations directly, we need to know the other properties of air as well. So let's take a look at how these air properties change with altitude, starting with pressure. So air pressure at any altitude in the atmosphere is determined by the weight of the air above that level. So this is easier to understand if you consider water. So let's talk about this case here. Suppose that you have a pool of water. So this is a pool with a certain height, h, and the pressure of water, the pressure formed by water depends on the altitude, right? So at the surface there is no water pressure because there's really no water above that level. But if you start going down the pool here, at any level, the pressure is determined by how much water you have above that level, right? Okay, so let's take a look at the pressure at at the bottom. Suppose that we have a cylinder here, and there's the surface, the area of the cross section is A. This is the area, and the force applied at the bottom due to the weight of this cylinder of water is equal to its weight times the gravity, right? So the force at the bottom is equal to mass times gravity, but mass is equal to the volume times density, and volume is equal to the area times height, A times h, right? So the force is equal to A times h times rho times g, right? So this is the force of the cylinder of water applying at the bottom surface, and the pressure is then going to be force divided by area, and that gives us rho times h times g, right? So this is the pressure at the bottom of the pool. So if you look at this, the results here, the pressure depends on the depth of the water, right? So that means if you increase the depth, then the pressure will be increased by the same amount. So there's a linear relation here. So if you measure the altitude with respect to the bottom here, and let this be h0, the height of the pool. So when we are at the bottom of the pool, h is going to be 0, and the pressure at this level will be rho times h0 times g, where h0 is the depth of the pool. But if you go up, when you come to the the surface of the pool, the pressure will drop to zero, right? At this point, the pressure is equal to zero. The pressure due to water. That will be the atmospheric pressure, but I'm just talking about the pressure of the water. So the relation is linear, right? So the atmospheric pressure is similar, but there's a very important difference, and that difference is due to the fact that air is compressible. So water is incompressible. That means the density of the water at this level is the same as the density at the bottom of the pool. But for air, that's not the case. So let me just read from here. Just like in a tank of water, air pressure at any altitude depends on the weight of the air above that level. But since air density also changes with altitude, to compute the air pressure, you need to take varying air density into account. Density increases with altitude. Density decreases with altitude, and it gradually becomes zero. Therefore, there is no boundary for air in the atmosphere, and hence there is no H value you can use for computing the pressure. So what I'm basically saying there is, if you have a tank of water, there's a certain height of water, right? And there's a level where for the depth of the water, but for air it's not true, because the air density decreases with altitude, and it gradually decreases, and as you come to a certain level, it gradually becomes zero. So there is no strict boundary for air. So in case of air, calculation of variation of pressure with altitude involves an integral equation that comes from the equation of fluid statics. So if you'd like to see how this equation is obtained, I can give you the derivation here. There's a PDF file here. I can give you this file, and in that file you can find the details of how air pressure as a function of altitude can be obtained. But I don't think that's really important. You don't really need to know the details. All you need to know for this course is that air pressure changes with altitude, and if air was incompressible, just like water, the variation with altitude would be a straight line as this one here. But since air is compressible, the relation is not such a straight line, but it is rather a curve that asymptotically goes to zero. And this is so this is zero, which represents sea level, and what you have here is the air pressure at sea level. And if you increase the altitude, if you start climbing, the pressure will be dropping, and it asymptotically converges to zero. And there's really no altitude level where the pressure becomes exactly equal to zero, as in the case of a compressible fluid. So here you know that the pressure drops to zero at a certain level, and this is the height of the fluid. But in case of air, the pressure asymptotically converges zero, like that. Okay, so this is how air pressure changes with altitude. Next, let's talk about the change of air temperature with altitude. Unlike pressure, there are no simple equations that give variation of temperature with altitude. However, experimental obtained measurements show that temperature variation with altitude consists of straight lines, as shown below. So temperature is important for both Reynolds number and Mach number. For Reynolds number, you need to know the viscosity, which depends on temperature, and for Mach number, you need to know the speed of the sound. That also depends on temperature. So for pressure, you know that pressure converges zero asymptotically, like this curve here. But for temperature, the relation is not that simple. In fact, the air temperature change with altitude looks something like this. So this blue curve here. So on a standard day, if the temperature at the sea level is this much, temperature changes linearly with altitude up to a certain level, which is about 11 kilometers. And then between 11 kilometers and 20 kilometers, it approximately stays constant. The air temperature doesn't change in this level. After that, from 20 kilometers to 32 kilometers, it increases. There's a slight increase. And then in this area, the increase is faster. And then there's another level where the air temperature stays constant again. And then it starts decreasing again. So there is such a temperature variation. And these different layers are given certain names. So the first layer, where the air temperature drops linearly by this slope, is called troposphere. And the next level is called tropopause, stratosphere. And these all have some special names. Well, I don't really know the physical reason of why temperature variation is like this, but it is a fact. And how do we know this? We know this from measurements. So from, I don't know when they first started taking such measurements, but so what people do is at the surface they set up a balloon. And in the balloon, they put some measuring devices, like the temperature sensor, pressure sensor, things like that. And they release this balloon to the atmosphere. And at different altitudes, they record these measurements. Okay? And when they looked at the measurements, it's how they found this variation. So obviously, there are physical reasons behind why the temperature variation is like that. But again, in this course, the only thing you need to know is there is such a variation of air temperature with altitude. Okay? So this is the same graph showing the variation of the temperature with altitude. So this, according to this website, this is the US standard atmosphere data from 1976. Okay, so let's review what we have so far. So we said that the air pressure change with altitude has such a curve, and you can calculate the equation for this curve using the fluid statics equation. The temperature variation looks like this, and there is really no equation for this. This is just based on measurements, and they're both given here as a function of altitude. This blue curve is showing the pressure change. The red curve shows the temperature change. And once you know the pressure and temperature, you can calculate air density using the ideal gas law, using this relation here. So once pressure and temperature are known, air density rho can be computed using this relation. Okay, so if I, for example, ask you to calculate forces at 10 kilometers, which is this altitude here, you need to know the pressure and temperature, which you can take from this curve, this data, for example, and then using these numbers, you can use those numbers in this relation, the pressure here, the temperature here, and you can calculate the air density, and that's what you are going to use in the aerodynamic force equations. Okay. So here's a summary of what I just said. The pressure comes from the fluid statics equation. Temperature comes from experimental measurements. And depending on these two values, the density can be calculated using the ideal gas law. So values of these parameters at different altitudes have been found according to standard atmosphere assumptions. And they are presented in standard atmosphere tables. So to study the performance of an aircraft at any altitude, you can simply take these values from the standard atmosphere table, which looks something like this. So in aircraft performance, we use these tables directly. Okay, so we don't really worry about how pressure changes and how temperature changes. We don't really worry about any of this data at all. What we do is we simply refer to these tables. So this table is, the altitude is given in terms of kilometers here. So 0, this is the sea level. And we have all these values given. So we have the pressure is here, the temperature is here, density is here. This is speed of the sound, viscosity, kinematic viscosity, they are all given in tables. So for example, if I ask you to calculate the force at 4 kilometers, what you need to do is you simply refer to this table and you say that at 4 kilometers, for example, the density is this much. And if you need to calculate the Mach number, you need to use this value for the speed of the sound. And if you need to calculate the Reynolds number, you should use this value for kinematic viscosity. Okay? And in fact, this is the value I used in the previous example. Let me show you that. Okay, so this value is 0.819. As you see, is directly taken from the table here. Okay, so in your future exams and homework problems, or whenever you need to make some aerodynamic calculations, you should use these tables, the standard atmosphere tables, and in the exams I will be giving you these numbers. Okay, so you can just take the number from these tables, and you can do just linear interpolation. For example, the table gives the values at 4 kilometers and 6 kilometers, but if you need to know the density at 5 kilometers, you can just take the calculate the corresponding number using linear interpolation. Okay. So obviously you should understand that these are just standard average values. Okay. For example, according to the table, at 4 kilometers the temperature should be this much in kelvins, but there's no guarantee that that will be the value. So if you make measurements at different days, and at night or in daytime, or if you measure in winter or in the summer, the values will be changing. But these numbers in these tables represent average values. And when designing an aircraft, we can this is what we use. Okay, so we can. So this is the best we can do in terms of predicting the air properties. So again, there's really no guarantee, obviously, that the air density will be exactly equal to this much. Okay, so this is what we use for air properties as a function of altitude, and in performance calculations, obviously these numbers become very important. For example, imagine an aircraft flying at a certain condition at sea level. To calculate the forces, you will be using this value for air density. This is the density at sea level. But if the same aircraft climbs to 10 kilometers, for example, at 10 kilometers, the force will be different. That's because the air density will be this much only. So this is about 34%. And so the ratio is given here. The sigma is density divided by sea level density. Okay, so at 10 kilometers, the density is 0.33756 times density at sea level. So obviously at 10 kilometers the lift force will be much less compared to the lift force at the sea level. It's only about 34%. Okay, so this is all I wanted to say today about air properties and standard atmosphere tables. Starting from next week, we will start performance calculations. So starting from next week, I will be talking about equations for longitudinal flight, and then we will start calculating the performance numbers. Okay? Are there any questions? So I will see you next week then.